to talk about standing waves. We're going to specifically talk about standing waves in a coil spring. So this is a phenomenon that happens if we have a medium, and this represents our medium. And if you remember, when an input wave strikes a fixed end, okay, the reflection of that wave is reversed, right? So if it comes in like this, it'll come out like that. Now this phenomenon, it happens in such a way that you can have input waves that look like this interfering the output wave. So in other words, you have this just oscillating up and down like this, okay? Now how much of an entire wave would this be, would you say? Half, right, because the whole wave would continue on to include the trough down over here, right? So just a couple quick definitions. L is the length between the fixed points, right, of this object. Now, as we increase frequency, right, we shorten wavelength, since for a given tension, the velocity is set. And we know V equals F lambda. So as frequency goes up, wavelength goes down. So if I continue to increase the frequency, I'll get some time where there isn't a standing wave, but then I'll hit a specific frequency where the wavelength is just right. And, oh, I changed color, and we'll get the next standing wave possible, which looks like this, okay? And you'll get this oscillation around where, you know, this is oscillating back and forth, and this is oscillating back and forth. Here, you have points where there is no oscillation, okay? So what this is, essentially, is incoming waves reflecting and interfering on their way back out. This would be an area of constructive interference. This of destructive interference. Okay? And they also have another name where there is no movement. We call these things nodes. So this has 3 nodes. N-O-D-E-S. And where this is constructively interfering, we call these antinodes. Pretty inventive, hey? And there's 2 antinodes here, okay? If we roll back up, here we have 2 nodes and 1 antinode. All right? And we'll do one more example, but then the pattern just continues, okay? So if this is our medium, okay, we are going to have something like this happening. This one ended up a little bit short, but they would all be the same size. So 3 antinodes, and 4 nodes. And it just continues this way on up, really, to essentially infinity. Okay. In terms of wavelength here, right? So here's L still, right? L is the distance from here to here. Okay. Well, in this case, L should be equal to the wavelength, right? This is one wavelength, and it's equal to L, the total distance between these 2 points. Are you with me on that? And let's just roll up and see if we can make an equivalent thing here. So here we have L. On this one, the length is equal to only half of the wavelength. Okay? Now here, what's L equal to? 1.5 wavelengths. So in other words, as the wavelengths get lower, right, we get more of them fitting into L. Does that make sense? And these correspond to a higher frequency. Now we have specific names for these types of frequencies that support standing waves. So this is a standing wave. And when the standing wave looks like this, when it's the lowest possible standing wave, whatever frequency that happens at, we call that the fundamental frequency. The fundamental frequency. okay? Also known as the 1' standing wave. Or first order is another way to say that. First order standing wave. Where would you see something like this, do you think? Think musical instruments. Yeah, a stringed instrument, okay, is essentially tuned so that the fundamental frequency corresponds to whatever note that is meant to be played, okay? So if you know this is the low E string on a guitar, say, you tune the tension such that that fundamental frequency matches the agreed upon frequency for an E note. Does that make sense? So when you pluck the guitar string, the main thing you will hear is the fundamental frequency, okay? And it buzzes away at that frequency and you hear the sound. You will also get these things going in the string at the same time. So not only do you have the major, you would also have these other secondary and tertiary and so on frequencies ringing at the same time. And this kind of gives you the timbre of the instrument. It's why you can tell the difference between, say, a violin and a guitar both playing E, or a bass guitar and a guitar both playing E. They could play the same frequency, exactly the same note, but you can tell a little bit just through how it sounds which one you're dealing with. That's got to do a little bit with what sub-frequencies are playing in there, okay? So this would be called the secondary standing wave. And another musical term that you might hear is this is also called the first harmonic, or the first overtone. So it has a bunch of different names depending on who named it. Physics, secondary standing wave; music, first overtone, right? The main tone and then the overtone or the harmonic. And then of course this will be the 3' standing wave, or the tertiary standing wave, or the third harmonic. Sorry, did I call that one the first harmonic? I did. Sorry, it's technically the second harmonic. My bad. And this is the first harmonic. Yeah, sort of. So it's sort of. This is what is essentially, so if you have a guitar, the guitar has like a large hollow chamber. What happens is the air in the chamber resonates with this frequency. Resonation, like you could say this string is resonating, but really, like in physics when we say resonating, we mean that something else is oscillating in tune with this. And in the case of a guitar, that's the air inside the body of the guitar, where you see it on violins, they have a body with sound holes. A drum has a chamber, so you bang on the drum, right? The sound gets amplified because of resonance. It's why an electric guitar, for instance, sounds really quiet if it's not plugged in. It doesn't have a resonance chamber. It doesn't have like the air to vibrate inside of it, so it sounds very quiet unless you amplify it. And let's just do one more quick example before we wrap this up. It's essentially the basics behind standing waves. So if I want, I could do, let's see. Oh no, it's the same one I just did, isn't it? Yeah, that's right. Okay. Oh no, I did one too many. Gosh darn it. So it should be 2 complete wavelengths in here, right? So I should be able to work through this. There's one. There we go. Got her. So do you see a pattern starting to develop here? The length of here started with a half, right? Start with a half. The length is equal to half a wavelength. The next level, the length is equal to 1 wavelength. Next level is equal to 1.5 wavelengths, and now it's equal to 2 wavelengths. And then 2.5, and so on up, okay? So there we go. And the number of nodes is always one more than the order of the standing wave. and the number of antinodes matches the order of the standing wave. People often, for some reason, get nodes and antinodes mixed up. Even myself, sometimes. I forget which is which, but nodes, no wave, antinodes, waves.